have some additional slides which are here called Advanced Measurement Configuration that will show you. There's hardware counters available on K-Computer, on FX10. We'll show you how to include those in the measurements that you get. You can get information available about resource usage coming from the operating system. It won't be complete information, that's operating system dependent, but we'll see what's available on the FX10. In principle, you can also get information from CUDA devices. That, of course, is not interesting on the FX10, but if it was a system with accelerators, you could configure SCORP with that support and enable such measurements to get information about the CUDA kernels, the data transfers to and from the device. One thing that we can also show you is the user instrumentation API that SCORP provides. We already saw that when we were instrumenting the code that it was using this user flag. That was the flag to enable the user instrumentation macros. We'll show you how those look in the source code as well. These define additional regions that show up in the analysis reports. You can define them as you choose. You can mark functions in that way if you don't want to use the compiler instrument to do that automatically. You can mark loops if these aren't parallel loops that OpenMP instruments. But you can mark phases or steps of computation at whatever level you like. If you do it at a very fine level of detail, you'll have more overhead, but that's under your control. The API is available for the different languages, Fortran, C, C++. You need to include the appropriate definition file. In this case, for Fortran, it's the SCORP user include file here at the top. You then mark the region, define the region to create a handle for it, and then you define the region having a begin and an end with that handle, some type information, some name information for that region, and then that will show up in the analysis report. The key thing to note here is that these macros require C preprocessing, so that usually means you have to use the capital F extensions for Fortran files or explicitly ask for them to be processed by the C preprocessor. For C and C++, it's a little bit simpler. You have a user.h file to include, but the way in which it's used is exactly the same. In this case, we're defining a solver region, a solver loop, and then marking it with the begin and the end around that loop. C++ is even easier again because you just need to mark the beginning of the region, and at the end of that scope, it will automatically be ended. So you don't have to. Otherwise, you have to take care that the begins and the ends match. In this case, with C++, it's automatically scoped in that way. There's also a control API that you can use that comes in the same header file that allows you to explicitly say that measurement should be disabled and then re-enable it when you come to part of the code execution that's more interesting. So this can be used to disable measurement during initialization or some part that's not so interesting, and then just include measurements for the entire solver or potentially just for particular iterations of the solver, particular time steps. So again, that's something that you can mark in the code and control. You can make it conditional based on the time step or the loop index or whatever you choose. You should do this with some amount of care to try and make sure that what you're recording is recorded consistently across the processes. If you're only recording the sends, then there can be problems with the trace analysis if you haven't recorded the matching receives for those. Or, for example, if you just record the broadcast on the master but not the broadcast on the other processes that participate in that communication. So all of these macros and for defining user regions and for controlling measurement are enabled by the SCORP --user flag. There's more information that we're not going to cover in detail here. You can do selective measurements of particular loops or particular parts of the code. Other features that could be interesting that I don't quite remember. They're all in the manual.
Yeah, but so maybe in the upcoming version, so we will have support for memory recording. which might be quite interesting. So there we capture all malloc frees, and therefore you just have to switch on one environment variable. So this might be of interest.
So I'll show you first the user instrumentation macro that was already incorporated into the source files that we were using here. It's inside this Scorpy user.f. So this is the Fortran 77 source code. This is the include of the macro. Here we actually guarded it so that we can compile the sources with and without it using this guard, Scorpy user enable. If we search further, we'll see the this is the definition of that. In this case, we're defining the main loop at the beginning. We are disabling recording during part of the initialization, just as an example here. Before we get to the interesting part of the computation, we're turning the recording back on again. The benchmark actually does an initial warm-up iteration before it goes into the main loop. So this is the main benchmark loop here. At the beginning of that, we're defining a phase or a region here. There's a number of different variations of this for different syntax, but we're defining something called an iteration here. And then at the end, we mark the end of this region. So within the parallel do loop, it shows up also in the measurements here. It's also used by Periscope for controlling the online measurement, but it shows up also in the measurements that we have here. So this is the iteration as we marked it in the source code. When we were building the application, we were using this flag, so that was the -- user here. If we didn't have this flag, then it wouldn't have been included. We could have customized the Scorpy instrumenter not to include the compiler instrumentation. No compiler would turn it off. Or there's various other customizations that could be used there to add memory instrumentation or other things. So here we're essentially using the default, but also using the user instrumentation. By default, it's going to instrument MPI. By default, it's going to instrument OpenMP. And by default, it's going to instrument the compiler functions, the user functions. This is something that we explicitly added here. And back in the measurement directory, this was the part of the execution where measurement was disabled. We still have the time for it, but we don't have any internal structure, any internal detail for that measurement. This was the iteration that was marked, so it helps us to isolate the benchmark kernel, which was part of that larger source file. So any part of the execution that's of interest to you that's not automatically distinguished is something that you can mark and include in your measurements. Okay. Don't want to do that. This one. So that was one way of getting some additional information into the measurement. Another thing that we could be interested in would be some hardware counters if those are available. PapiAvail tells us that there's a number of counters that are available here on K-Computer. Here it's actually telling us the counters which are available for the front end. For the host, that's not actually interesting for us. We actually want the counters that are available on the compute nodes. That's not so easy to get. You'd have to start a job or an interactive session and then run PapiAvail there. I'll skip you the tediousness of that, but you could do it yourself, or we can do it and show you the results later. I know that there are various counters available. I'll just use one that I know is available, such as Papi floating point operations, and add that to our measurement. While I'm at it, well, let's... so here we have an example where it's using two counters, one for floating point instructions and total instructions. I guess I haven't tried that combination, so let's try it right now. I'll just give it a different name so that it stores the results in a separate directory. Actually, while I was there was some other stuff I wanted to add. So there's also these are usage metrics. I can specify them individually, or I can choose something else here. I think that if I say all, that should give me all of the available metrics. Actually, it will give me all of the defined metrics, and we'll see which of them are available. Okay, so let's submit this. You don't need to do this yourself unless you feel motivated to do so. Obviously, you should expect that the more metrics that you add, the more overhead you'll have during the measurement. That's part of the trade-off that's unavoidable. So, of course, it's important that you do the filtering first. The filtering is the main controller of overhead. But if you add additional metrics, if you add additional counters, that will increase the amount of data that's collected. It will increase the measurement overhead. Well, that wasn't expected. No idea what happened there. Did it actually produce something? It produced some sort of profile?
So sometimes the PAPI is not, or we're not able to shut down PAPI properly. So this might come from this.
Okay, so we got a measurement. We have the basic information for a measurement as we had before. In addition to the basic measurements, we have two PAPI counters, total instructions and floating point instructions. And we have those values collected for each process, for each thread. And we can see how those vary across the execution call paths as before. So we'll probably find that, the parts of the code that take the most time are also the parts where there's more instructions executed. And this is a fairly floating point intensive code, so a large subset of that is for floating point instructions. So when we are looking at the profile of execution time and comparing that to total instructions or floating point instructions, it's a little bit heavier in the computational kernel for those, but it's more or less the same distribution in this case. We also have the additional our usage metrics here. This is user time, which will be essentially the same as execution time in its distribution. The system time for I/O operations or for other activities. Various counters are not available, so these are not provided by the operating system. We are getting the number of page faults, I believe this is. Soft page faults, page reclaims, and context switches are these other counters. So you can select which counters are available and are interesting to you and potentially include those in your measurements, whether these are hardware counters or usage counters. And by defining when you collect information, you can add additional structure or disable measurements when it's not so relevant for you. So those are things that you can experiment with as you wish. Okay. So far, we have been doing profile measurements, runtime summarization, where we aggregate information from the execution across all of the instances of the call path to create these call path profiles. We'll move on and look at what we can get with Scholastica from Scholastica trace analysis. So let's look at the slides for this.